Hello everyone, today we're going to talk about the free body diagram and all about it. So, to understand what a free body diagram is and what it kind of asks you to do, let's think of one of the most simplest things that can happen. So, let's say you have a table, it should be straight, so a table, and a box on a table. The box has some kind of kilogram on it, like it can be 5 kilograms, but let's just call it mass for now. Like it's kilograms, and what you also should know is that the sum of the forces that apply on the box equal to mass times the acceleration of the box. So, however, the box is stationary, it's not doing anything, like it's not moving, it's just there, which means that it's not accelerating, because when it accelerates, that means that it's moving somewhere, it has a movement. So we know that things that are stationary, like right now, let's say you're on a table, like that bottle that's near you, it's stationary. The acceleration is 0, and like whatever the mass is, like anything the mass is, that means like even if it's like a million, okay, let's just do 100 times 0, it will be equal to 0. So we know that, for example, the sum of this force of the box, it's equal to 0, because 0 equals to 0. However, that doesn't matter that much. It does, but what the point of this video is free body diagrams. So what we should understand that when we do a free body diagram, we get the main event. So let's say right now the main event is the box. So right now we're talking about the box. So we don't care about the table. We don't care about the earth. We don't care about anything. Like there could be like another planet right near there. We don't care about it. We care only about the box because that's the main event. So when we draw a free body diagram, we draw a box and we draw the forces that apply on it in this situation. So the box is like the force of Earth is pulling the box down, which is the weight. So we can just put W for weight. However, we know that weight equals mass times gravity. And we also know that the box is applying a force itself, pushing itself from the Earth, which is the normal force. So there's also a normal force, and that's all the forces that are there. However, just quickly for you to understand, so even though the box is on a table, and the box itself, it is applying a force to the table, like let's say like the floor, right, the table on its own, that like the mass of the table and the weight of the table is different than the one with the box, because the box adds up in weight. However, even though like we don't care about it, we care only about the main event. So you have to screw that in your brain that, okay, the question is about the box. It can be about a cat, like there can be a cat on the table. You don't care about anything else apart from that cat. So you just have to understand that when you do a free body diagram, you do mostly one event happening. So remember, like it's not accelerating, it's doing nothing, and these two, they are parallel, they're equal to each other. So know that these two added, they cancel each other out and it equals to 0. And just quickly, heads up, basically, let's say if you're asked to draw about this whole thing, you should not like draw it like the free body diagram like this. These two objects, they are separate. Yes, you're talking about them, but you have to make two different free body diagrams, because they both have different, like you can't do that. It will be a mess. Like you have a force applying to this, and then a force applying to this, a force applying to this. It won't work out. You have to do them separately. So over here we have an example question. Draw a free body diagram for the following situation. A box is dragged across the floor at a constant velocity. the box is being pulled by a rope horizontally, and there is an opposition to the forward pulling force by friction. So, first of all, let's draw what's happening, but like not in a free body diagram way. So, we have the floor, right? A box. Something is pulling it. Let's say a person, like just a person, he's pulling it, or she. And there's friction. Friction is because of the floor. So we'll draw it somewhere here. And we know that this block, whatever it is, it has some type of weight. So we'll just put like weight, the gravity force on it, and then the normal force, because to have it balanced, because again, if there would be no normal force, it will just keep going, like it will just squash or whatever. So this is how it kind of looks like that, like without, but this is not a free body diagram. So again, the pull force and the friction force, which you can just put as like big F, small f. So the free body diagram would look something like this. So the box, nothing done, it's in space, nothing around it. The person, he's gone. So we just put the pulling force. The floor's gone. We could draw like the friction force here, but like we don't need to in a free body diagram. So like this, then the weight, and then the normal force. So that's how it is. And last time I said that acceleration means when it's moving, so it has some type of acceleration. Like remember, like forces add up equal to mass times acceleration. However, I said that in the wrong way. So over here the box is dragged at constant velocity, which means constant velocity means like it's going 1 meter per second, for example. Every second it goes only 1 meter, not slower, not quicker. That's how fast it goes, which means it doesn't have any acceleration. Acceleration is when it gets bigger or kind of slower, all that type of stuff. So which means the acceleration equals to 0 because it's not there. It's going constantly, constant velocity. So over here we can see that we have two like we have horizontal and we have vertical. So what we're able to do, if just so we know what to do in these types of situations, so we can write fx equals to ma x because is the same thing, like it's just for the x's. So we know that these two, so this one is making it move, however this one is what's not letting it move, like as fat, like kind of cancelling it out, like the friction of the floor. So we know that if the acceleration is 0, so the acceleration is 0 in this situation, then these two, they are equal. Because if this one was like a bigger number value, then it would be accelerating. However, it's not, because you have to understand that, let's say you are like just moving something and it becomes, and you start moving it like on a different surface. Let's say right now you're moving, I don't know, a pen on a table, and then you like, okay, not a pen, a bottle on the floor or on the carpet, it will stop moving quickly. However, on ice, that won't happen. It will like continue more faster because there's less friction in ice. However, so we realized that these two, they should be equal because they cancel each other out to give us 0, because so we tend to think that on the right side it is a positive, on the left it's a negative. So we're also able to say that these minus force pull equals to 0. So they are equal, because if it's equal to 0, it's equal because like 1 minus 1, for example, is 0. You can have 1 minus 2 equaling to 0. That will be minus 1. That can't happen. And then the horizontal, the vertical, well, we don't know that it's on the floor and it's not moving as if like up and down. It's not going like crazy, like it's not jumping or whatever. So we're also able to say that these two, because it's balanced, it's not going whoa, 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 whoa. No, it's on a balanced, it's in its balance moment. We're able to say that the weight take away the normal force is also equal to 0. So yeah, that's everything. Thank you. Goodbye.